Oh, that's okay. Good. Afternoon. Welcome. Has anyone not been before? So you all know where the toilets are. Good. Don't have to do that again. As usual, we're not expecting a fire alarm test. So if the fire alarm does sound, please leave in an orderly manner out of the door through which you entered and gather in the piazza outside until somebody tells you what to do next. Anyway, well, thanks for braving the slightly dodgy weather today. I wasn't quite sure what was going to happen when I saw the amount of rain coming down this morning, but there we are. And thanks for coming out on a non-standard day and time for that matter. I don't know why we have standard days. I'll have to look into that. But anyway, thanks for coming along. Our speaker today is Professor Nick Achilleos from the astrophysics group within UCL's Department of Physics and Astronomy, where he's director of UCL's Centre for Planetary Sciences, and he's Vice Dean of Equity, Diversity and Inclusion for UCL's Faculty of Mathematical and Physical Sciences. Nick's current research interests broadly cover the magnetospheres and ionospheres of giant planets, so Jupiter and Saturn, and how those systems are coupled together. He's been a mission planner for the team who managed the magnetometer instrument on board the Cassini spacecraft, and he's also a science co-investigator for the JMAG magnetometer team on the Jupiter Icy Moons Explorer mission, known as JUICE. Well, they have to be called something, I suppose, which is due to arrive at Jupiter in 2031, which is probably when my next bus will arrive, I suspect. Nick's going to talk to us today about some of the important discoveries about the magnetospheres of both Jupiter and Saturn, and some of the science goals of the JUICE spacecraft, which will, as we said, be there soon, in due course. Anyway, over to you, Nick. Thank you.
Thank you. Good afternoon, everyone, whether you're here in person or online. So today, what I'd like to talk to you about is magnetospheres of these worlds that I've listed here. And along the way, we're going to explore this by sort of going through different aspects. Let me see if I can get this working. Yeah. Okay, so we'll start off by introducing general aspects of the magnetospheres of the gas giants, Saturn and Jupiter, in particular the properties of their magnetic fields, and also what goes hand in hand with magnetic field and space environments of these planets, including the Earth, is the plasma. So plasma is the so-called fourth state of matter. We don't find it very commonly here in our day-to-day lives on the surface of the Earth, but essentially it's gas that's fully ionized, where the molecules or the atoms have been separated into their component positively charged nuclei and negatively charged electrons. And of course, once matter exists in that state as electrical charges, it feels very strongly the influence of any magnetic fields or electric fields that may exist in its environment. We'll also briefly look at the Jupiter-Ganymede interaction, which is a very complex subject, but it's one of the prime science goals of the JUICE mission, which Peter mentioned. And in particular, what makes it complex is that Ganymede, of course, is one of Jupiter's so-called Galilean moons, but it's the only moon in the solar system that has its own substantial internal magnetic field. So Ganymede carries its own mini magnetosphere with it around inside the magnetosphere of its parent planet. So it's a very interesting thing to look at. And along the way, I'll show you examples of magnetometer data from missions such as Galileo, and also come back to JUICE, the Jupiter Icy Moon Explorer, a mission led by the European Space Agency, which launched in April the 14th of 2023, and will arrive at the Jovian system in 2031. And I believe in August of this year, it's going to perform a flyby of the Earth-Moon system to pick up some extra energy that it needs to get out into the outer solar system. Okay, so to sort of set the scene, here is a comparatively simple table showing a comparison between our world, the Earth, which is this sort of small planet way down here, in comparison with the size of Jupiter and Saturn here with its famous set of rings. So in these columns, we've got some fundamental physical parameters of these worlds. And you can see that, you know, compared to the Earth's mass, if we set it equal to 1 unit, Jupiter's more than 300 times the mass of the Earth. And Saturn is pretty impressive, almost 100 times the Earth's mass. Both gas giants have radii something like 10 times that of the Earth's 6,500 kilometers. But for their size, they rotate very rapidly. Both rotational periods for Jupiter and Saturn are less than half an Earth day. So they carry a lot of angular momentum in the language of physics. In terms of magnetic field, the intrinsic strength of the source or the internal currents that create a planet's magnetic field can be simply sort of quantified through a parameter known as the dipole moment. And this is essentially the strength of the magnetic field at the equatorial surface of the planet multiplied by the third power of its radius. So it's field strength times radius cubed. And if we set that equal to 1 for the Earth's numbers, Jupiter's dipole moment is a whopping 18,000 times as strong as that of the Earth, and Saturn's is several hundred times as strong. So these are incredibly strong magnetic fields. Why are they so strong? We believe that part of the reason is their rapid rotation, and part of the reason is because at the enormous interior pressures that these worlds have, hydrogen exists in a very exotic state known as a liquid metal, which becomes an almost perfect conductor of electric current. Another interesting aspect arises if we look at the latitude of the magnetic pole of these worlds. Now, we know that here at the surface of the Earth, we have magnetic poles, which over the course of centuries can wander about on the surface of the Earth a little bit, but typically the Earth's magnetic axis or magnetic pole is separated from its geographical pole or its spin axis by an angle something like 10 degrees. So the latitude of the magnetic pole is something like 80 degrees for the Earth. Similarly, for Jupiter, it has a similar dipole tilt. Saturn is really interesting because as far as we can ascertain, the magnetic and spin axes of Saturn are parallel to within a few hundredths of a degree. And that's a very unusual result. It's certainly not a result that you expect if you speak to, you know, dynamo theorists who study the generation of internal planetary fields. So that's a very strange, unexpected surprise. I think I need to go down here. Oh, I see now. Yep. Right. Okay. So here's some interesting representations of magnetic fields of different worlds from an overview by Jerry Schubert and Krista Soderlund. And the idea here is that what you're seeing on a color scale here is just the radial component of the magnetic field at the surface of these worlds. So the radial component, of course, is just that part of the field that points outwards from the center of the planet. So on the top left here, for example, you've got Mercury, then Ganymede, then Jupiter, and this concentration of strong radial field here is, of course, the magnetic pole. Uranus and Neptune, very complex patterns compared to the dipole fields of the other worlds. We believe that these are complex because the seat of the magnetic dynamo is closer to the surface of the planet. So at the surface, you see the more sort of the more sort of complex parts of the field more easily. Saturn here, as you can see, is just a series of horizontal lines. So that just really suggests, as I said before, that the magnetic axis and spin axis are parallel. The spin axis of all the planets in this representation is simply a vertical line in the plane of the page. Now, at the time that this picture was created, the model for Saturn's magnetic field that we showed here was by construction an axisymmetric or zonal magnetic field model, axisymmetric about the axis of rotation. Even when later data came in and we looked at how much the field departed from axisymmetry, it wouldn't really change much from this picture. The planet's internal field is axisymmetric to a very good degree of approximation. So that raises the question, why? Yeah. Oh, you've got a
It'll come
hand.
up, yeah. Do you want to just click
Yeah.
on the X and kill it?
Okay,
What's the thing?
that's the participants.
Yeah.
I'll just
kill
I'll
that.
just remove it.
Yeah.
Okay,
Sorry.
all right. Okay, so there's been a lot of discussion, as you can imagine, about why Saturn has such a rotationally symmetric field. And one of the most convincing explanations that I know about actually was formulated by Dave Stevenson back in the 1980s, inspired by spacecraft data which existed at that time from missions such as Voyager and I think Pioneer. So I won't go into too much detail here, but the idea behind his idea is that Saturn's interior structure exists in a very special regime of temperature and pressure. And in particular, what happens is that you have outer layers of the planet here, which are rich in helium, and that helium slowly rains down into closer to the center of the planet. And when I say rain, I don't mean like a rainstorm that you'd walk through here at the surface of the Earth. I mean drops of liquid helium that formulate and fall over geological timescales. So it's a very slow process. But as a result of this process, Stevenson hypothesized that the interior layers of Saturn, where the magnetic field or where most of the magnetic field is generated, would be surrounded by what he called an inhomogeneous layer. And the idea here is that this layer rotates at a slightly different rate from the interior layers. And in doing so, it actually removes any non-axisymmetric terms in the field that the planet itself is trying to generate. So in physics, this is related to a thing known as the skin depth effect, where if you have in your frame of reference what looks like a magnetic field component that's oscillating, and you would see that if you were rotating at a slightly different rate compared to the field itself, then, if you have a conducting layer surrounding the seat of that magnetic field, it removes all the non-axisymmetric or oscillating terms in your frame of reference. So his idea was that Saturn, in fact, is creating a typical magnetic field with a dipole tilt and with non-axisymmetric terms, but it happens to be in a unique regime of interior structure where a so-called screening layer is formed surrounding the dynamo region that literally removes the non-axisymmetric terms, and only the symmetric ones can survive up to and outside the surface of the planet. And only those terms can be observed by our spacecraft. So much later, scientists such as Sabine Stanley, who simulate the formation of magnetic fields on computers, seem to confirm through their calculations that this indeed could be plausibly what is happening at Saturn. Okay, and forward. Okay, now let's jump back to consider the magnetic field of our own world, the Earth. So on the left here, we have a cartoon of the so-called geomagnetic field of the Earth. And in the cartoon, we see that to a good degree of approximation, the field lines that you see on the surface are what you would expect as if a giant, strong bar magnet were buried somewhere in the interior of the planet itself. So this compass needle represents the orientation of the magnetic poles, the south magnetic pole joined to the north magnetic pole up here. And these magnetic field lines represent the classical so-called dipole pattern, which exists when your system is dominated by two magnetic poles. So those are the magnetic poles. They are tilted at a certain angle with respect to the geographic pole, as you can see here. And that means that whatever that angle of tilt happens to be determines where on the Earth's system of geographic latitude and longitude you would observe that magnetic pole. So on this diagram here, we've got a representation of how much the north magnetic pole has wandered on the surface of the Earth over the past couple of centuries or something like that. So we've got in particular a very interesting phenomenon going back to 30 years ago or something like that. And we've got, in particular since then, you can see that it's wandered quite considerably in latitude and longitude on the surface of the Earth. So this is a very difficult motion or wander to predict, because physically speaking, the nature of the magnetic dynamo, the combination of conducting fluid and turbulent motions and rotational motions that create magnetic field, is a chaotic system. You know, you only need to change the initial conditions of the dynamo by very small amounts and you would get a very different looking field. So it's a very difficult system to predict what it's going to do. Indeed, additional observations at the Earth's surface of the ocean bed, which is magnetized according to whatever the magnetic field happened to be at the time of that rock forming. That kind of evidence shows us that the magnetic pole shifts position, like shown here. But not only that, the polarity of the Earth's magnetic field, the north and south magnetic poles, actually flip around over geological timescales. And it's very difficult, if you look at that geomagnetic record, to predict exactly when that's going to happen. There seems to be no rhyme or reason to it. So that's kind of an interesting aspect as well. Now, if a planet like the Earth, Jupiter, Saturn has a magnetic field, it's almost certain that it's also going to have an aurora. Now, the aurora at the Earth is what we call the northern or the southern lights, the aurora borealis or the aurora australis. So here's a photograph of auroral emission in the Earth's, I think this is the northern polar or the Arctic regions. And typically in the night sky of a country such as Iceland, Norway, or even Scotland sometimes, you'll see this very intriguing green glow, or there can be other colors, which looks like almost like curtains in the sky waving around very slowly. So what causes this? We know from many observations and investigations that the source of this energy is actually energetic electrons from the planet's space environment or magnetosphere. So for the Earth, those particles have energies of motion up to about 100 keV, kilo electron volts, which is the energy that would be picked up by an electron, you know, moving through a potential difference of 100,000 volts. So it's a considerable amount of energy. So these energetic particles rain down onto the planet's upper atmosphere. They excite resident atoms of oxygen that exist in our atmosphere. And this occurs at altitudes about 100 kilometers or above, where the electrons deposit most of their energy. So those excited oxygen atoms, once they relax back down to their de-excited state, they radiate characteristic wavelength photons of light. And it just so happens the energy difference between these quantum states corresponds to green color of light. You can get other colors from other transitions associated with aurora, such as characteristic blue and pink colors associated with nitrogen and other elements. Not only can you get electron precipitation or rain producing aurora, you can also get aurora that arise from proton precipitation. The energetic particles come from the space environment or the magnetosphere. And at the Earth, and indeed at other planets, we know that most of the acceleration of these particles to these high energies occurs in the short distance just before they enter the parent planet's atmosphere. Okay, so here's a cartoon of what I've just been talking about. You've got the Earth surrounded by the magnetic field lines of its mainly dipolar field pattern, and you've got electrons and ions in the ambient space environment or magnetosphere being funneled down along the magnetic field lines. These particles follow the direction of magnetic field lines. So you can have quite a wide expanse of electrons and ions very far from the planet, but because of the way the field lines converge much closer together as you approach the magnetic poles, at the end of the day, what you see is rings of excited auroral emission that surround the north and the south magnetic pole. Okay, so I've been mentioning a magnetosphere space environment. So what do I actually mean by magnetosphere? So here's what's hopefully a useful picture that helps us think about it. If we were sort of sailing along on the surface of a lake or an ocean in a boat, in our frame of reference, where the boat seems to be stationary, we would of course see water moving towards us from upstream. And we would also see that water kind of slide around the obstacle that we and our boat present. And in fact, if we kind of look behind us to either side of the boat, we would see these interesting features known as bow waves, which is a sign of the water rearranging itself as it tries to move around this obstacle. So for the magnetosphere, you can apply similar thinking, but this time the boat is ourselves living on the Earth and the magnetic field that surrounds us. The fluid that flows towards us from upstream comes from the sun and is known as the solar wind. It's a plasma outflow from the corona of the sun, which consists mainly of protons and electrons with a few helium nuclei. So this plasma, as it flows towards our boat, tries to slip around the obstacle that not only the planet presents, but also the magnetic field of the planet, because magnetic fields, we know, deflect charged particles. They impose forces on charged particles. So that's an important aspect of this interaction. The obstacle is not just the planet, but also the magnetic field of the planet itself. Now, the solar wind is moving so quickly, by the time it reaches Earth's orbit or, orbits in the outer solar system, that the only way that the solar wind plasma can be successfully deflected is for it to be literally shocked into submission. In other words, the equivalent of the bow wave for the boat now becomes a shock wave standing off upstream of the planet itself, which very abruptly compresses and slows down the solar wind. So the magnetosphere is the cavity inside this deflected flow of solar wind plasma. And the boundary of the magnetosphere, which is often called the magnetopause, generally speaking, separates the magnetic field and plasma sources of the planet and its local environment from those of the solar wind. Magnetic field is also carried around away from the sun in the solar wind flow. All of this suggests that planets with magnetic fields are very special because that magnetic field shields them from the ravages of the solar wind. A good example of planets which don't have this kind of shield is Venus and Mars. And we know that at Mars, for example, the solar wind has eroded much of the Martian atmosphere over the eons, which is why the atmosphere at Mars is so thin and low pressure compared to that of the Earth. Let's look now at Jupiter's magnetosphere. So here's a cartoon. There's a lot going on. So Jupiter itself, remember, Jupiter is 10 times the radius of the Earth. Jupiter is this small brown dot here in this diagram to give you an idea of scale. And what we have here is a two-dimensional slice through a three-dimensional system. So the purple region is the magnetosphere, and in 3 dimensions it forms a shape, something like a bullet or a paraboloid shape about the planet, about the parent planet. And what we have here is a slice through the noon meridian on the day side, facing the sun, solar wind flowing in from the left, and the midnight meridian on the night side. Black arrowed curves represent magnetic field lines. So you see magnetic field lines close to the planet have this Earth-like dipolar shape. But we know from observations that when you get to a region called the middle magnetosphere of Jupiter, something like 10 to 40 or 50 Jupiter radii from the planet, the dipole field lines become pinched out radially along the equatorial plane. And that's because of the presence of an additional source of magnetic field, which is this yellow region known as the current sheet. This is a slice through the current sheet, but the current sheet you can think of as a disk of plasma, an enormous disk of plasma that surrounds the planet and stays close to its magnetic equator. And the ultimate source of plasma for that disk or for that current sheet is Jupiter's volcanic moon Io that you see here. Now, Io is, its surface looks like a pizza. It's kind of dotted with volcanoes. And these throw up compounds of sulfur and oxygen into the space environment. Those compounds or molecules become ionized through radiation from the sun, or usually from impact with energetic electrons in the magnetosphere, and they form a plasma, which is rich in charged states of sulfur and oxygen. Now, that material can't build up indefinitely near the orbit of Io, or more correctly, the region near Io's orbit, which is anchored to the magnetic equator, known as the Io plasma torus. That stuff has to go somewhere, and it diffuses outwards through the system on a scale of tens of days, diffuses outwards very slowly, forming this more extended, what we call magnetodisk that surrounds the planet, which merges into, on the night side, what we call a magnetotail current sheet. And the magnetotail earns its name because on the night side, as you can see, the magnetic field lines are drawn into these long tail-like shapes. Why? Because one end of them is anchored to the planet and the other end opens out into the solar wind, which of course is moving continually past the planet and dragging that end of the field line with it. All right, so this is all well and good, but how do we actually know that this picture is real and that these current sheets and plasma sheets exist? One way that we know is because for a planet like Jupiter, because there's a tilt between the magnetic and the spin axis, that means that the magnetic equator is also tilted with respect to the rotational equator. And as the planet rotates, the magnetic pole is like a magnet, the magnetic equator is like a magnetic tilted plate that wobbles around because it follows the magnetic equator, not the spin equator. So we expect to see that wobble somehow in observations that spacecraft make of these kinds of systems. And before I go on to that, this is a cartoon just showing that if you could see the magnetic field lines of Jupiter's magnetosphere in the night sky, they would look something like this, and in angular size, be larger than even our own moon, just to give you an idea of the size of this enormous magnetosphere. Right, now, here we go. So here is an animation that's going to illustrate, I hope, in a better way what I've just been talking about, the fact that as the planet rotates, it carries around this structure here, the Io plasma torus, anchored to not the spin equator, but the rotating tilted magnetic equator. And if you keep looking at the animation, this little moon here is Io, and here we have Europa. And what you'll see as the animation proceeds is that if you were someone living on the surface of one of these moons, you would see the magnetic field structure wobble up and down past you as the planet rotates. So sometimes, as you can see, you're inside the Io plasma torus, sometimes you're below it, sometimes you're above it, depending on, the phase of the rotation and of the moon, and also the phase of rotation of the planet, which carries around the tilted magnetic field and the Io torus with it. So sometimes you're above the plasma sheet and you see magnetic field pointing away from the planet. Sometimes you're below and you see magnetic field pointing towards the planet. And sometimes you're right inside, which by definition is where the field lines are changing direction. And you see no radial field component. So with that in mind, we can move on and look at some actual data. This writing up here is not supposed to be here. Something's gone wrong with the slide, but never mind. What you see at the bottom of the slide is real spacecraft magnetometer data from missions that have visited Jupiter. So on the left, you've got data from Voyager 1, and on the right, you have data from the Galileo spacecraft, which orbited Jupiter from the mid-90s. I think it was 1995 till the early 2000s. So I won't go into too much detail, but essentially going from the top to the bottom, you've got the three components of the magnetic field, and down here, you've got the magnetic field strength as a function of time, as measured by the magnetometer instrument on board these spacecraft. Now, the field has three components because it is of course a vector. It's a quantity that has both magnitude and direction, and it's three-dimensional, so you need three numbers to fully represent it. However, a person studying current sheet dynamics, our favorite field component is the radial component. Why? Because as you can see, when you have orbits like these, which are skimming around close to the rotational equator of Jupiter, you see the radial field periodically changing direction, or equivalently changing algebraic sign. Positive for pointing out of the planet, negative for pointing back into the planet. So these sort of flat tops on this square wave represent times when you are just above or just below the current sheet. When B radial passes through zero, that's when the center of the plasma sheet is passing over you, or the spacecraft more correctly. Now, you can see that superposed on this nice, steady periodic pattern, there's also smaller scale features that indicate other interesting dynamics. But essentially, the periodic behavior of B radial is evidence of the presence of a rotating, tilted plasma sheet that carries a fair amount of current, just by itself. You can see that in the Galileo data, you also have periodic variations in VR, but at some point they seem to vanish. And confusingly, in this representation of the Galileo data, the spacecraft is getting further from the planet as we go from right to left. So in the outer magnetosphere, the periodic behavior of B radial goes away. Now, people think that behavior like this is because you're entering a part of the system where the thickness of that plasma sheet increases. And if it increases enough, it means that the tilt of the tilt of the system, if the plasma sheet's thick enough, even a tilted plasma sheet the spacecraft will never fully leave the plasma sheet if it's very thick. If it's a very thin one, you'll make clear passages above and below it, as you see in the Voyager data. But in regions over here where the plasma sheet suddenly becomes thick, the spacecraft finds itself continually trapped inside, even though this thing is still tilting around. It's so thick that it contains the spacecraft all the time. So even these sort of basic clues give you, insight into some very interesting dynamics of the system. Okay, so that's a little bit about the shape of the plasma sheet itself. How fast does the plasma move inside that plasma sheet? Here's some of the earliest data from plasma instruments that answers that question. So on the left here, we've got Galileo plasma data measuring the speed, the rotational speed of the plasma as a function of distance from the planet. Jupiter is here at the origin. I don't know if you can see, but the scale represents distance in Jupiter radii. This is the night side of the planet. This is the day side. You can see the arrows getting much, much larger. The velocity arrow is getting much larger as you move radially outwards. And indeed, that's because you're traveling, the plasma's rotating at really high speeds, hundreds of kilometers per second. Close to the planet, within about 20, 30 Jupiter radii, the plasma co-rotates with the parent planet perfectly. Once you get further out, the communication of momentum from the rapidly rotating planet to the surrounding magnetosphere is less efficient, and the plasma exhibits what we call sub-co-rotation. Similar observations here from Voyager, showing rotational speed on the vertical axis as a function of time or distance here on the horizontal axis, with a convenient line representing perfect co-rotation with the planet. So here at the comparatively small distances, 15, 20 Jupiter radii, you're close to perfect co-rotation, and then the observed velocity peels off from perfect co-rotation as you go further out into the magnetosphere. Now, all these velocities that you see in the plasma observations are enormous compared to what they would be if only gravity was acting on the plasma. They are enormous compared to a so-called Keplerian orbit. And that's important because it shows clearly that in systems such as these, gravity is not by any means the main thing determining the dynamics. It's electromagnetic interactions that determine the dynamics. All right, another mystery about Jupiter's plasma is why is it so hot? So here's from Peter Delamere and Fran Bagenal's study. of basic plasma properties at Jupiter. They collected data from Galileo in green and Voyager in black, which represents the temperature of the plasma in units of electron volts as a function of radial distance in the equator. So you can see that according to their curve of best fit here, generally speaking, there is scatter in the measurements, of course, but generally speaking, in an average sense, the temperature increases with increasing distance. This is contrary to physical intuition because we would expect that as the plasma migrates outwards, it occupies larger volumes because it's anchored to the magnetic field, and the magnetic field becomes weaker, which means magnetic flux is spread out over a larger area. That suggests that temperature should decrease, the plasma should cool. But you can see that at least for much of this profile, it's heating up. And people are still trying to understand what causes that heating. There are ideas from Kivelson and Southwood, for example, that try to connect the rotational energy of the planet to the thermal energy of the plasma. So that's another mystery. Let's now have a look at Saturn. At our group, we've had lots of very talented students, looking at these kinds of spacecraft data for their thesis work. One such student was Ariana Sorba, and part of the work that Ariana did was to look at data such as the data I've been showing you, the oscillating magnetic field component from the current sheet, but for Saturn, not for Jupiter. So Ariana was looking at data from the Cassini spacecraft. So the components of the field in these three panels, the observations from Cassini are in black, and you can see that our favorite field component, B radial, has this intriguing sawtooth-like pattern. And the green and the blue curves are mathematical models that Ariana put together to try and match the data. Mostly we were successful, but of course nature is more complicated. So we weren't always able to get agreement like you see here, but some important results that came out from this work are two results. The first is this sawtooth pattern arises because Saturn's plasma sheet does not have a uniform thickness. Its thickness depends on the longitude where you happen to be as the plasma sheet rotates. So in other words, the plasma sheet passes over Cassini twice per rotation when BR passes through zero. When BR takes longer to make the transition from below to above the current sheet, that happens because, of course, the plasma sheet's thicker. Half a period later, you're on the thinner side of the sheet, and the transition is much quicker, and the gradient in the BR curve is much steeper, which leads to this sawtooth pattern. And the other important result is that we definitely needed that modulation in plasma sheet thickness to explain the phase relations between this component of the field, known as the B theta, or the axial component, and the radial component of the field. So Saturn is a really strange system as far as these aspects are concerned. The other thing I haven't mentioned, but is also worth mentioning, is that I said in the beginning quite correctly that Saturn's magnetic and spin axes are parallel. Now at Jupiter, the wobble in the current sheet is caused by the tilt between magnetic and spin axes. So why is it that we see oscillations in the field in Saturn's outer magnetosphere, but the planet's magnetic field is actually symmetric about the rotation axis? How does it impose tilt on the magnetosphere? That's a good question. It's been the subject of a lot of studies, such as the ones shown here. And to keep things quite general, we believe that the reason we see tilt in Saturn's current sheet is there's a special system of currents that couple together the planet itself, the ionosphere of the planet, to its outer magnetosphere. This is an example of what we call magnetosphere-ionosphere coupling, an extraordinarily complicated process, many aspects of which we are still trying to understand. Okay, so we're coming into the closing stages now, so I'll turn now to JUICE and the prime science target of JUICE, which is the moon Ganymede, some of whose surface you can see here in an image taken by the Juno spacecraft currently in orbit around Jupiter. So Ganymede is something like 5,500 kilometers in diameter, which makes it larger even than the planet Mercury. It orbits Jupiter at a distance of something like 15 Jovian radii from the center of Jupiter, with an orbital period of something like 172 hours. At its orbital radius, the orbital motion, the orbital velocity of Ganymede is really slow compared to the rate at which plasma rotates past Ganymede, because the rotation rate of the plasma corresponds to Jupiter's period of 10 hours. So you've got plasma rotating really quickly past this moon. So Ganymede sees different faces of Jupiter's magnetic field as the parent planet rotates. And because that field is due to not just the internal source of the planet, but also the plasma sheet, it sees these wobbling field components. So let's have a look. And here's a bit of a digression, and I'll explain why I'm telling you about this in just a moment. But when we have a moon like Ganymede exposed to different faces of a magnetic field of its parent planet as a function of time, that can lead to a phenomenon known as electromagnetic induction. So this diagram here shows us an example of one of Faraday's original experiments that demonstrates this phenomenon. So we have here a battery on the right here that drives a current through a coil of wire labeled A. So once you drive, a current through a coil of wire, you create a magnetic field. It's essentially a solenoid. So this is a magnetized object. You jiggle it up and down inside another coil of wire, which is labeled B. This coil of wire is not attached to any battery or any type of electromotive force. It is attached, however, to G, a galvanometer, which detects current flow. Now, when you jiggle the magnetized object, or more correctly, the magnetic field up and down inside coil B, this is a conducting body, and it sees different magnetic field, or more correctly, different magnetic flux as a function of time. Faraday's law tells us that a change in magnetic flux translates to an induced electric field in the conductor, which drives the current. And indeed, when you do this experiment, you will see the galvanometer detect current, even though coil B is not connected to any battery. The only thing that's causing the current to flow is the change in magnetic flux due to you jiggling A, source of magnetic field, up and down inside coil B. So why is this important for Ganymede? It's important for Ganymede because we believe from Galileo, there is some evidence that Ganymede might be showing this effect. It might be exhibiting the magnetic field associated with an induced signal, probably because it has a conducting subsurface ocean. So here is current picture for the interior of Ganymede, an iron core where its own magnetic field is formed, surrounded by a rocky mantle, and then some layers of ice and water. And somewhere in there, there's a saline ocean that capable of conducting electrical current. So this conductor, if it's exposed to different faces of Jupiter's magnetic field, changing magnetic flux, you'll drive a current through that ocean. That particular current in the ocean generates what we call an induced magnetic field signal, which contains clues as to what the ocean's made of, how deep it is, how thick it is. That induced magnetic field signal is what JUICE is looking for. And if you think it's not going to be trivial to find it, you're absolutely right. So here we have the driving field from Jupiter, or the inducing field that Ganymede is exposed to. This is the different components of the field. You'll see that the amplitude of change in one of these components is something like 100 nanotesla. That's the main variation along the Jupiter-Ganymede direction projection of the field. At Ganymede's surface, the corresponding induced field at most will correspond to this amplitude of 100 nanotesla if the surface ocean is something close to a perfect conductor. But if we compare that maximum 100 nanotesla from the induced signal to Ganymede's own field, that's something like 700 to 1400 nanotesla, depending where on the surface of Ganymede you happen to be. So we're looking for an induced signal that is a small fraction of Ganymede's own surface field. And you can play the game of creating models of the field of Ganymede, and in particular, how Ganymede's own field connects with Jupiter's ambient field to which it's exposed at different phases of Jupiter's rotation. So I won't go into too much detail, but essentially here's a picture of what you get if you do that kind of calculation. And what arises, interestingly, here is different regions of what we call magnetic field topology. This is Ganymede. When you're close to this Ganymede surface near the equator, you see a region of these closed green field lines which commence and terminate on the surface of Ganymede itself. Above and below Ganymede's poles, you have half-open field lines, if you want to think of it that way, where one end is anchored to Ganymede and the other end, way off the scale of this plot, connects to Jupiter. Outside this cylinder, which is essentially a magnetosphere of Ganymede, you have blue field lines which belong entirely to Jupiter, which commence and terminate on the surface of Jupiter itself. Now, the presence of the induced signal, the induced dipole, has effectively perturbs Ganymede's own field by shifting Ganymede's poles by 2 degrees or less, and changing the magnetic moment of Ganymede by a paltry 0.1%. But these are the effects that we're going to be looking for with the JUICE spacecraft, and the magnetometer is capable of detecting that level of perturbation. What makes it complicated, of course, is the magnetic fields from all the other sources in Ganymede's environment. So this is a cartoon of what we're looking for, the induced field signal arising from Faraday's law in a conducting subsurface ocean. What complicates this, of course, is that you have on top of this the moon's own dynamo-generated permanent field. And not only that, but all the currents arising in this very complicated interaction between Jupiter's field flowing in here from the left with the plasma that co-rotates with Jupiter, and Ganymede's internal field. So for example, you have the formation of this sort of cylindrical or quasi-cylindrical magnetosphere, which has these characteristic boundaries upstream and downstream, which also form current sheets. So essentially, we're trying to tease out a small needle from a very large haystack. And just to finish up, I'll mention a little bit about people at UCL who are involved in the JUICE mission. So here are some examples of the instruments on the JUICE payload. And let me see if I can go forward. The instruments where we have involvement in particular are JMAG, the magnetometer. The Principal Investigator Institute is Imperial College, led by Professor Michelle Doherty. And some of my colleagues at the Mullard Space Science Laboratory, which is part of UCL, have involvement in the plasma instrumentation package known as PEP, the Particle Environment Package, which will look at the distribution of energies in the particles comprising the plasma, wherever the spacecraft happens to be taking observations. So spacecraft was launched April last year. It will arrive in July of 2031, and in December of 2034, it will enter its Ganymede orbital phase. It will change from being a dedicated orbiter of Jupiter to being a dedicated orbiter of Ganymede. And doing many orbits of Ganymede, we hope, will provide us with the most detailed magnetic map of Ganymede's environment, from which we hope to understand more about Ganymede's interior structure. Here's some of my colleagues from Cassini, from the end of Cassini mission in 2017, where we were with great anticipation looking at the last orbits of magnetic field data from the Cassini spacecraft. Cassini data set is still being studied by people. And finally, I'd like to dedicate this talk to my colleagues from Cassini, Claudio Alexander and Giacomo Gamperi, who unfortunately are no longer with us, but who were incredible people to work with. Thank you for listening. Thank you.
Thank you, Nick. I'll never look at a bar magnet the same way again.
And quite rightly too.
Questions, please. Here you go.
A thought crosses my mind to maintain the attitude of the satellite, are you still using gas jets and inertial spinners, or have you thought of actually using the magnetic field itself via a solenoid arrangement? I would have thought something like a superconducting disk or a set of 3 of them would solve. It would play hell with your magnetometers, of course, while you're actually doing the adjustment.
Yeah.
But once you've done them, the energetic costs are 0.
Okay. Well, as far as I know, the attitude of both Cassini and of Juice is going to be controlled through engine burns and a system of reaction wheels on the spacecraft. We like to keep the magnetometer as free as possible from contaminant magnetic field, which is why the magnetometer on a spacecraft is often situated on a long boom extending out from the side of the spacecraft. So we like to keep it as magnetically clean as possible. But one thing that the navigation team with Cassini were particularly good at doing in order to conserve fuel was they were able to use moons of Saturn as what they called tour engines to change the orientation of spacecraft orbits. So if you're visiting a system which has conveniently placed moons, you can use those as a means of changing, the spacecraft tour as well.
Any other question? I've got one. Actually, I've got 2. You mentioned the Earth's magnetic poles wander around and occasionally flip. So they wander around on timescales of kind of years. How long does it take for it to flip?
I think if I remember correctly, I think to perform a full flip, when that happens, it's of the order of tens to hundreds of thousands of years at least. Something like that.
So it's a sort of extensive wandering.
Well, it's when the flip happens, in principle, you can say, oh, the magnetic poles just change position, and on that level, it's conceptually easy to understand. But when you actually look into the details of what that involves, it's almost like the field is turning itself inside out, and that's because of lots of complexity that's going on with the current systems inside. Yeah.
Okay, another one. I don't know. I may be off beam here, but you mentioned in Jupiter's the plasma temperature increases as you go further away from Jupiter, which is puzzling. Is that in any way related to the phenomenon of coronal heating on the sun, where I think a similar thing kind of happens? The corona is much hotter than we think it ought to be.
My understanding is that some of the latest pictures which try to explain the coronal heating from the sun look in particular at wave particle interactions. So in plasmas, you've got, of course, particles whizzing around in response to electric and magnetic fields, but the perturbations in the plasma from an equilibrium state also generate waves. And it's very complex, but the waves and the particle population can exchange energy. So a lot of people have looked into wave particle interactions at the sun as a source of plasma heating. Now, wave particle interactions also happen at Jupiter, so it may be that they're part of the explanation. But an explanation I'm more naturally drawn to is people who talk about somehow tapping the rotational energy of Jupiter itself, because there's so much of it available to heat the plasma. And you can do it through this process. In principle, you can do it through this process of magnetosphere-ionosphere coupling, setting up currents that flow between the planet and the plasma. So which picture is right? I guess we'll eventually see. Maybe it's a combination of both.
Thank you. Anything else? Pat, have we got any questions online? No? Okay, well, if that's it, I'll say thank you once again, Nick, for coming and giving us a fascinating insight into magnetics.
Thank you, it's a pleasure. Thank you.
Oops, I just have to say something about next. What's happening next? Sadly, I'm afraid I haven't been able to engage a speaker for next month. So there won't be a talk in April, and unless I can pull a rabbit out of a hat, although it will need to be a talking rabbit, of course. So our next scheduled talk is on the 30th of May, when Dr. Erminia Calabrese will tell us about the cosmic microwave background. And apologies that we haven't got all the details on the website yet. She's away somewhere. So anyway, tune in for that. Anything else? Appeared on.
Yes.
So for the benefit of the people online, a question has appeared from Kang Lee. Thank you for that. What is the cause of the formation of neutron stars' extreme magnetic fields? And Nick is typing a response to that, which he will presently read out.
So I don't know a huge amount about neutron star fields, but neutron stars are an example of stars where the matter inside is incredibly dense and compact. In fact, the star is kind of like a giant atomic nucleus. It's incredibly dense, compact matter. So we call that degenerate matter, and the combination of that form of matter. And I think, again, coupled with rapid rotation of pulsars, which are rotating neutron stars, I think is part of the reason for the strong fields. And the other aspect of that is that some people believe that, yes, and some people believe that, a star can start its life, as a sun-like star, which has a solar level magnetic field. But at the end of its life, if it's compacted into a tiny volume, that affects the field strength as well, because the magnetic flux that's spread over a larger volume, it's like you're pushing field lines into a much closer volume. So that also amplifies the field.
Okay, thank you. So that's all for today, folks. Thank you very much for coming, and see you next time. Bye-bye.